Usually when we look at the cutting edge of technology, we kind of expect to see something, well, something metallic.
Right.
Cool.
Like engineering.
Exactly. You think of silicon chips, sterile data centers, endless rows of servers blinking in the dark. It all just feels very rigid.
Yeah, it feels binary. I mean, it's mathematical and completely distinct from anything biological.
Yeah.
And, we often find comfort in that separation. We categorize our machines as tools that operate on strict, unfeeling logic, completely divorced from human nature.
But then you step into the foundational blueprints of modern artificial intelligence, and suddenly that cold metallic image just evaporates.
Oh, completely.
Because we're looking at a blueprint today for this deep dive that is, honestly, it's squishy.
Squishy is a good word for it.
Right. We are tracing the staggering intelligence of modern supercomputers all the way back to a biological concept from, 1957. How did an artificial brain start with a punch card machine?
Well, to answer that, we are looking closely at Chapter 4 of the Artificial Intelligence Primer. And this is published by ISACA, which, for those unfamiliar, is a major global association for IT governance and cybersecurity professionals.
Right.
This primer really breaks down the absolute bedrock of AI. And our specific focus today is neural networks.
Which is huge.
It is. Because if you want to grasp the tools transforming our world right now, from, chatbots to predictive models, you have to understand the microscopic building blocks. I mean, you can't understand the ocean without studying the water molecule.
Okay, so let's unpack this. Where did the idea for an artificial brain actually come from?
Yeah.
Because before we can look at the math and the code that power machine learning, we kind of have to look at the physical reality of our own heads. The primer starts by asking a really simple question for you to consider. How do humans actually learn?
Right. Think about the last time you tried to understand a complex theory or solve an intricate problem for the very first time. You don't just instantly download the correct answer into your brain.
No, I usually stumble around in the dark for a while, make a few terrible guesses, and try again.
Exactly, which is the core mechanism of biological learning. We iterate.
Right.
Knowledge builds over time through this process of trial, error, and adjustment. We start with simple foundational concepts, and we gradually grow more complex. I mean, if you touch a hot stove, you experience an error pane, and you adjust your internal settings to change your future behavior.
Hopefully, yeah.
Right. And artificial neural networks, or ANNs, were conceptualized to replicate this exact iterative process.
And this brings us to a researcher named Frank Rosenblatt.
Yes.
It's 1957, and I just want to set the scene for a second.
Yeah.
1957 is the year Sputnik launched.
Oh, wow.
Computers are the size of entire rooms. They run on vacuum tubes that generate massive amounts of heat. You have to program them using physical paper punch cards.
That's a very different world.
Yeah, it's a highly mechanical, rigid, tedious era of computing.
Yeah.
But Rosenblatt isn't looking at the punch cards. He's looking at human biology.
Yeah, what's fascinating here is that he was completely captivated by the signal processing abilities of biological neurons. He wanted to build an artificial neural network for early image recognition. And he realized the most logical step to building machine intelligence was to mimic the physical architecture of the only intelligent system he actually knew.
The brain?
Exactly. So to do that, he designed a concept called the perceptron.
The perceptron. It sounds like a 1950s sci-fi movie villain.
It really does.
But it is literally the seed of all modern AI. To understand it, the primer breaks down the structure of a biological neuron. Your brain has billions of these. So let's look at the anatomy.
Right. So from figure 4.1 in the text.
Yeah, we have the cell body, which contains the nucleus. We have dendrites, we have the axon, and we have synapses.
And the audacity of Rosenblatt's vision in 1957 just cannot be overstated. He looked at that microscopic biological structure and envisioned translating its flow of information into a mathematical model.
Okay, I need to visualize this flow of information. Let's imagine a single biological neuron is like a really busy office worker. Let's call him Bob.
Okay, Bob, the office worker.
Right. Bob's entire job is to sit at his desk and make one single decision over and over again, to send an email or not send an email.
So a binary classification task. It's a strict yes or no output.
Exactly. So Bob has an inbox on his desk. In the brain, these are the dendrites.
The receivers.
Right, the receivers. They are constantly piling up with memos and signals from neighboring neurons or, other office workers.
Sure.
Then you have the cell body, the nucleus. That's Bob himself, sitting at the desk, reading all these memos, processing the information, weighing how important each message is.
Right, and once he processes that information, he has to communicate his conclusion to the rest of the network.
Yeah, so if he decides the information warrants action, he uses his outbox. In the biological neuron, this is the axon,
The transmitter.
the transmitter of signals. He fires his decision down the axon, and it travels out to the synapses, which are the intricate connections linking his outbox to the next office worker's inbox.
Right.
Dendrites receive, the cell body processes, the axon transmits across synapses.
And that flow of information is exactly what Rosenblatt formalized with the single-layer perceptron. We are basically transitioning from the biological reality of the office worker to a mathematical equation a computer can calculate.
Okay, so I'm looking at the anatomical formula of the perceptron provided in the text here, and I have to admit I might need a translator for this part.
It looks a bit daunting at first.
It's an equation that essentially reads W times I plus B. And then all of that runs through something called an activation function, represented by the letter A.
Right.
So walk me through that. What are we actually looking at?
Let's break those variables down piece by piece. First, we have I, which stands for inputs. Just like the dendrites receiving signals, the mathematical perceptron needs data coming in.
So if we go back to our office worker, the inputs are the raw memos landing on the desk.
Yes.
Let's try to map this onto a real-world decision to see how the math actually plays out. Let's say, think about deciding whether or not to buy a used car.
Good analogy.
You're standing on the lot looking at a vehicle.
The
The inputs, the I, are the raw objective facts about the car.
data.
Right. Fact 1, the mileage is $100,000. Fact 2, the price is $5,000. Fact 3, the color is, I don't know, bright neon green.
But raw facts alone don't lead to a decision, right? Which brings us to the next variable, W, or the weights.
Okay.
The primer explains that weights determine the influence of the input. In your brain, a biological connection might be physically stronger or weaker depending on how important a signal is.
Right. Some memos matter more to Bob.
Exactly. In our equation, the perceptron assigns a numerical weight to each input to represent its importance.
Here's where it gets really interesting. The weights are how much you personally care about each of those facts. Let's say you are on a very tight budget.
So price is key.
Price gets a massive weight. It influences you heavily. The mileage gets a medium weight. But the color, maybe you don't care about aesthetics at all. So the neon green input gets a very low weight, maybe even 0. You multiply the raw fact by how much you care about it. That gives us our W times I.
And the perceptron then sums all of those weighted inputs together to calculate the total value of the incoming information. But there is a crucial missing variable here.
The B.
Yes, B, the bias. The text notes that the bias provides flexibility in fitting the model.
Wait, if we already multiplied the facts by how much we care about them, what does the bias actually do? Are we just, like, artificially inflating the score?
Well, in a way, yes. The bias represents a baseline threshold or predisposition. It shifts the entire activation function up or down completely independently of the inputs.
Let me see if I have this right. The bias is my inherent baseline mood before I even walked onto the car lot.
Exactly.
Let's say my current car literally exploded this morning.
Oh, terrible day.
I am desperate. I need a car today. So my internal bias is incredibly high. Even if the weighted inputs of the car are just mediocre, maybe the price is a little high and the mileage is just okay, my high bias might push the final mathematical score over the edge to buy it.
That is a highly accurate translation. It's your starting point. Alternatively, if you already have a great car and you're just window shopping, your bias is negative. It's going to take a perfect combination of inputs and weights to get you to buy. So you take the sum of the inputs multiplied by their weights and you add that baseline bias.
Okay, so I've crunched the numbers in my head. W times I plus B. I have a final score. Let's say the final number is 10, but I haven't actually signed the paperwork yet.
Which brings us to the activation function, denoted as A. This produces the final predicted output, which is often written as he hat. Now, in biology, a neuron doesn't just leak a continuous stream of weak electricity. It builds up an electrical charge until it hits a specific threshold, and then it fires a definitive impulse.
It bops.
Right. The text calls this the biological action potential. And the mathematical activation function mirrors this perfectly. It is the strict mathematical gatekeeper.
So the activation function looks at my final score of 10 and says, is this high enough to act? It basically acts as a threshold.
Yes.
It might say, if the final number is greater than 0, output a 1, fire the signal, buy the car. If the number is less than 0, output is 0. Stay silent, walk away.
Precisely. It evaluates that weighted sum plus the bias and decides if the artificial neuron fires or stays silent. It translates a continuous spectrum of possibilities, all that complex math, into a concrete binary decision. This sequence is how a single artificial neuron processes information.
It's just wild to think that this simple calculation is the spark of artificial intelligence. But we have a problem.
Oh.
Our artificial neuron just calculated its weights, evaluated its bias, crossed the activation threshold, and made a decision to buy the neon green car. What if it was a terrible decision? What if the car breaks down a mile down the road?
Ah, right. Because an artificial neuron can make a decision, but intelligence isn't just making decisions. Intelligence is learning from the wrong ones.
Exactly.
A perceptron has to have a mechanism to realize it made an error and adjust its internal parameters.
But how does it do that? If it's just a math equation, how does it know it messed up?
Through the perceptron learning algorithm, during what we call the training phase, we provide the perceptron with historical data where we already know the correct answer.
Okay.
We show it the data for the neon green car, and we, as the supervisors, already know it's a lemon. The perceptron looks at its initial, randomly assigned weights and bias, does the math, and says, output 1, buy the car.
And we step in and say, incorrect, you bought a lemon.
Exactly. The system identifies an error. The output was 1, but the target was 0. So the learning algorithm executes. The fundamental rule is to change the weights and the bias in the direction that reduces that error.
Right, because it said yes when it should have said no.
Right. So the algorithm goes back and lowers the weights of the inputs that led to that bad decision. It mathematically penalizes the pathways that caused the mistake.
So it tweaks its own internal settings. It basically says, okay, next time I'm going to assign a lower weight to the cheap price and a higher weight to the mileage.
Yes, and this happens iteratively. The primer emphasizes that this process is repeated for each training example, perhaps thousands or millions of cars, until all are correctly classified or a stopping criterion is met.
Right.
But there is a vital control mechanism governing this adjustment, and it's called the learning rate, or alpha.
Alpha. Yeah, the text says the learning rate controls the size of the change made to the weights and biases during each iteration.
Right. When the perceptron realizes it made an error, the math tells it which direction to adjust its weights. The alpha rate determines how drastically it changes those numbers.
Okay, I have a critical question for you, the listener, to ponder here.
Yeah.
If our goal is to get to 0 error as fast as possible, why don't we just set the learning rate to be massive?
That's a good question.
Right. If the perceptron guesses wrong, why take tiny microscopic baby steps with the weights? Why not take a giant mathematical leap toward the right answer to speed up the training?
Because setting a massive alpha is incredibly dangerous for the algorithm. Imagine you were playing a game of miniature golf.
Okay, miniature golf.
You are standing on the green and you are trying to put the ball perfectly into the hole. That hole represents 0 error, the perfect set of weights and biases. Your learning rate, your alpha, is how hard you swing the golf club. If your alpha is massive, what happens when you swing?
I hit it way too hard and the ball flies right past the hole to the other side of the green.
Exactly. The algorithm will overshoot the correct weights. Mathematically, instead of changing a weight from a 10 to an 8, a massive alpha might swing it from a 10 to a negative 50.
Oh, wow.
You've overcorrected. The equation is now broken in the opposite direction. When it tries to learn from the next mistake, it swings massive in the other direction again. It bounces wildly back and forth from one extreme to the other without ever settling into the optimal solution.
So the overall error of the system might actually increase.
Yes, it just destabilizes.
Okay, so giant leaps are bad because we blow right past the answer. Let's go to the other extreme. I'll just barely tap the golf ball. A tiny, tiny alpha rate.
Well, if the learning rate is too small, your ball barely moves an inch. It will take you thousands of strokes to reach the hole.
Right.
In computing terms, your network takes a massive amount of time and resources to learn, inching painfully toward the correct weights. It might even get stuck in a small dip on the golf course. A local valley of error, thinking it has reached the lowest possible point when the actual hole is still far away.
Finding the perfect learning rate is a delicate, crucial balancing act for anyone training a model.
It really is.
It's like the Goldilocks zone of machine learning. Not too big, not too small. So our perceptron has its inputs, its weights, its bias. It has its activation function to act as a gatekeeper. And it has the learning algorithm with a perfectly tuned alpha rate to correct its mistakes. I mean, it sounds like a flawless system.
It does sound flawless, but it actually harbors a fatal mathematical flaw.
A fatal flaw.
Yeah. To understand it, we have to visualize what the perceptron is actually doing to the data when it makes these decisions. This introduces the concept of decision boundaries.
Okay. We mentioned earlier that the perceptron is primarily used for binary classification tasks. Yes or no, buy or don't buy, apple or orange.
Right. To accomplish this binary split, the mathematics of the perceptron draw a decision boundary. This is a line, or in higher dimensions, a flat surface that basically separates different classes of data points. You can see this in figure 4.4 of the primer.
Visualize a piece of paper with a scatter plot graph. You have a bunch of dots clustered on the left side and a bunch of dots clustered on the right. The perceptron's entire job, its only mathematical capability, is to draw a straight line right down the middle of that paper so that all of Group A is on one side and all of Group B is on the other.
And the major limitation here is that the perceptron learning algorithm can only succeed if the data is what we call linearly separable, like in figure 4.5.
Let me ground this with a physical example. Picture this. You drop a handful of M&Ms on a table. Half are green, half are blue. They scatter. If they happen to scatter in such a way that all the green M&Ms are clustered on the left side of your table and all the blue M&Ms are on the right, you can take a straight wooden ruler, place it flat on the table, and perfectly separate the two colors.
And in that scenario, the data is linearly separable. A straight line divides them perfectly. The single-layer perceptron calculates its weights, draws the line, achieves zero error, and its job is done.
But what if we aren't just dealing with a flat table? You mentioned higher dimensions earlier. Something about a hyperplane. What does that actually mean?
Right, so when you have more than two inputs, say hundreds of variables about a car, you aren't drawing on a flat piece of paper anymore. You are operating in 3D space, or higher. Imagine taking a 3D room full of floating M&Ms.
Okay, floating M&Ms.
The perceptron can't use a ruler. Instead, it uses a hyperplane, which you can visualize as a giant, infinitely flat sheet of glass. It tries to slide that flat sheet of glass through the room to separate the green from the blue.
So a ruler on a table or a flat sheet of glass in a room. Either way, it is completely rigid and completely straight.
Exactly, which leads to the fatal flaw.
What if the green M&Ms form a ring, like a complete circle, and the blue M&Ms are sitting right in the center of that ring? They are completely surrounded. Try separating them with your straight wooden ruler now.
You can't do it.
You can't.
Yeah.
No matter where you place that straight edge, you're going to have green and blue M&Ms on both sides of the ruler. A straight line is entirely useless.
And this raises an important question, right? This exact problem caused a historical crisis in artificial intelligence research, often referred to as the start of the AI winter.
The AI winter?
Yeah. Researchers in the 1960s realized this mathematical limitation. The real world is incredibly messy. Real-world data like the visual complexities of a self-driving car navigating a street, or the nuances of human language, the chaotic fluctuations of the stock market, it's rarely perfectly linearly separable.
The real world doesn't neatly cluster on the left and right. It's full of circles and squiggles and overlapping chaos.
Exactly. And because a single-layer perceptron's equation represents a strictly linear function, it can only draw straight lines or flat sheets of glass. When faced with data that forms a circle, like your M&Ms, or a simple logic problem called an XOR gate, its usefulness hits a hard wall.
It just fails.
It cannot learn the pattern. It will loop forever, tweaking its weights, swinging its golf club, trying to draw a straight line through a circle, and it will continuously fail.
When people realized that this supposedly miraculous artificial brain was defeated by a circle of M&Ms, funding basically dried up. People gave up on neural networks for a long time. It's a pretty depressing chapter in the history of computing.
The AI winter stalled progress for years. But, and this is the exciting part, the mathematical wall was eventually broken. If a single perceptron can only solve linear problems, the solution was to scale up, to move from the single biological cell to a complex tissue.
We stack them. We take thousands or millions of these single-layer perceptrons and we wire them all together.
Yes. This is the multi-layer perceptron, or MLP. It's also referred to as a feed-forward network. And as you can see in figure 4.6 of the primer, the architecture for this structure consists of three main components: an input layer, one or more hidden layers, and an output layer.
So what does this all mean? Let's go back to our office building analogy. Before, we just had Bob sitting at a single desk, receiving memos, drawing a single straight line. But Bob couldn't handle complex circular problems, so management buys an entire skyscraper.
I love this analogy. Okay, so the input layer is the ground floor. It receives the raw initial data from the outside world, the pixels of an image or the audio frequencies of a voice command.
Then you have the hidden layers. These are the middle floors of the skyscraper. And the primer notes something critical about the architecture here. The network is fully connected. What does fully connected actually mean for the workers in our skyscraper?
It means massive interconnectivity. Every single office worker on floor 1, the first hidden layer, processes their individual equation and sends a copy of their final outbox memo to every single office worker on floor 2.
Wow.
And every worker on floor 2 calculates their own weights and bias and sends their decision to every single worker on floor 3. It's an immense web of communication.
But wait, how does stacking a bunch of people who can only draw straight lines suddenly allow the skyscraper to draw a circle? If everyone is fundamentally limited to W times I plus B, how do we escape the straight line?
By layering these simple boundaries on top of each other, they approximate curves. Think about it. A circle is essentially an infinite number of infinitely small straight lines. By combining hundreds, thousands, or millions of these straight-line decisions, the multi-layer perceptron can wrap its decision boundaries around any shape of data.
Oh, that makes sense. Let's use a face recognition analogy to see how this layered approximation works in practice. So the ground floor of our skyscraper receives a photograph. The workers there are just looking at raw individual pixels. They pass their data up to hidden layer 1. The workers on hidden layer 1 are specialists. They use their straight lines just to look for very basic contrasts. A sharp edge, a patch of light, a patch of dark.
They find the fundamental boundaries of the data space.
Right. They pass those basic edges up to hidden layer 2. The workers on the second floor combine those edges, a curved edge from one worker, a shadow from another worker. Suddenly, hidden layer 2 is identifying a texture or a complex shape like a nose or an eye. They pass that up to hidden layer 3. And hidden layer 3 combines an eye, a nose, and a mouth and concludes that is a human face. They pass it to the output layer at the very top of the building, which makes the final classification.
Exactly. The network is isolating those complex patterns by drawing a multifaceted polygon around them with multiple intersecting lines from all those different neurons. This is the basic form of a deep neural network.
But wait, I have a massive mechanical question here. We talked about how the single perceptron learns. It makes a mistake, looks at the error, and tweaks its weights. But in a skyscraper with 1 million workers, how does it learn? If the output layer at the top of the building incorrectly identifies a picture of a dog as a human face, how do the workers on floor 2 know they need to change their weights? They are miles away from the final decision.
That is the core mechanical challenge that had to be solved to end the AI winter. The network uses a process called backpropagation.
Backpropagation, propagating backwards, so the error travels in reverse.
Yes. When the output layer makes a mistake, the network calculates the total error. Then the algorithm moves backward through the layers. It essentially performs a complex calculus of blame.
A calculus of blame.
Yeah.
Like that. So the boss on the top floor yells down to the floor below, "We messed up. Who sent me the bad data?"
That's pretty much it. The top floor assesses which connections from a layer below contributed most heavily to the wrong answer. It tells the specific neurons to adjust their weights downward. Then, those neurons look at the layer below them and pass the signal down again, adjusting the weights of the connections that misled them.
So the blame cascades all the way down the skyscraper, floor by floor, until every single worker has slightly adjusted their internal bias and their incoming weights to ensure that specific mistake doesn't happen again.
It is an incredibly elegant, mathematically dense choreography. And the primer makes a point to emphasize that despite this massive skyscraper scale, the core mechanics at the microscopic level have not changed at all.
Right. Every single neuron in that massive multi-layer perceptron, whether it's looking at a raw pixel on floor 1 or assembling a nose on floor 50, still relies on its own individual weight, its own bias, and its own activation function.
Every single node is still just processing W times I plus B.
It is the exact same equation Frank Rosenblatt was tinkering with in 1957.
Yeah.
We would just have billions of them working in concert, passing blame backward and passing straight lines forward.
Exactly. And if we connect this to the bigger picture, this fully connected multi-layer perceptron architecture is the gateway to all advanced AI.
Yeah.
Once you have this foundational structure, data scientists start modifying it. You can build convolutional neural networks which specialize in advanced image processing by altering how the layers scan data. Or recurrent neural networks, which introduce loops of memory for understanding language and processing time. But it all stems from this architecture.
The sheer volume of these simple connections is what actually creates the illusion of intelligence. By densely layering these tiny equations, the network can fit almost any data distribution imaginable. It can finally learn the chaotic, squiggly lines of the real world.
It is the profound shift from a single, rigid calculation to a dynamic learning ecosystem.
Let's take a breath and recap this instructional journey. We started with the squishy reality of the human brain dendrites receiving signals, cells processing them, and axons transmitting them across synapses. We watched Frank Rosenblatt in 1957 map that biology to a simple mathematical equation. Inputs times weights plus a bias running through an activation threshold.
Right. And we examine how that single equation learns by making mistakes, identifying its error, and adjusting its internal dials. We explored how that adjustment is carefully governed by the delicate alpha of the learning rate, ensuring it doesn't wildly overcorrect or get stuck.
We found the perceptron's ultimate limitation. It could only draw straight lines or flat hyperplanes. It was defeated by the chaos of circles and nonlinear data. And finally, we shattered that limitation by stacking them. We built the fully connected, immensely powerful multi-layer perceptron, allowing it to approximate the curves of the real world through millions of tiny, interconnected straight lines.
It really is one of the most remarkable structural evolutions in the history of technology.
It is. I mean, you have to realize that every piece of magical AI you use today, every time a chatbot writes a poem for you, or an image generator creates a masterpiece, or your phone recognizes your face, it owes its entire existence to this exact evolution. Beneath the sleek interface, it is just billions of biological mimics sitting at their desks, calculating their weights and biases.
Which brings us to the philosophical edge of what we've unpacked today.
Yeah. We want to leave you with a lingering question to mull over. If stacking these simple mathematical mimics, just adding more hidden floors to the skyscraper and more intricate connections, yields the astonishingly complex and seemingly creative AI we interact with today, at what point does a massive quantity of simple mathematical connections become indistinguishable from true understanding?
Right. If our own human brains are ultimately just a vast network of interconnected biological neurons firing action potentials based on chemical weights and biases.
Then is artificial intelligence simply a matter of building enough hidden layers? We'll let you think about that. Thanks for joining us on this deep dive.